I brought along my son Jonathan, who in the year 2001 will be the same age as I am now. Maybe he will be better adjusted to this kind of world that you're trying to portray.
The big difference when he grows up, in fact, if we wanted to wait for the year 2001, is that he will have in his own house, not a computer as big as this, but at least a console.
It's now 2024, and while it's been over 50 years since Arthur C. Clarke first made this remark regarding computers, I think it's worth investigating how we got here and where we're going next.
The numeric data which is to be processed in a computer is usually written out on a card data form before being punched onto a computer card. The printed figures along the top of the card are not read by the computer, which instead scans each vertical column for punched holes. Thus, the number 3 in the first column is represented by a rectangular hole punched in row number 3. Similarly with the other numbers punched 1 per column. Decimal points are represented by multiple punching in the same column. Multiple punching in the same column is also utilized to represent alphabetic characters. Here we see a typical Fortran coding form and a Fortran punched card. The Y, for example, is represented by holes punched in 2 different rows. It is not at all necessary to learn the code in order to operate a card punch.
These tiny transistors are destined to play a big part in our electronic age. They will make possible smaller, more compact electronic devices that will need less maintenance and have a longer life. But to grasp fully the importance of these new members of the electronic family, let's recall the wonders made possible by the high vacuum tube, the common radio tube. The roots of the electronic age reach back into the early years of our century.
This work on transistors can largely be credited to a one Claude E. Shannon. His pioneering work revolutionized the burgeoning field of electronics and information theory with his seminal 1948 paper, which continues to inspire innovation today. However, the importance of his earlier master thesis, a symbolic analysis of relay and switching circuits, cannot be understated as it laid the groundwork for Boolean circuitry, in other words, the use of ones and zeros to represent information.
Imagine, if you can, an electronic brain operating at millionths of a second speeds. I say brain because the new electronic central office will almost think for itself.
UNIVAC, the giant electronic brain made only by Remington Rand, takes business statistics from magnetic tape, letters, numbers, and punctuation marks, processing them through its electronic circuits at phenomenal speeds. UNIVAC can compute payrolls electronically, then produce printed checks in a flash. Over 8,000 checks an hour with this high-speed printer. UNIVAC leads the field of electronic computing.
There's the machine, and I'm supposed to talk to it. I say talk, but it's more a matter of writing it little notes, type little memos into it. Of course, there are a large number of what computer people call languages, but they don't seem much like any language we humans speak.
But Johnny's idea made this basically possible. What is the stored program concept? Well, it's the notion that you can describe in a finite number of words, in fact, a fairly small number of words, in a fairly simple language, exactly and unequivocally the description of a problem. And that this description is then translated into binary digits and stored in the memory of the computer exactly as numbers are stored.
So where does that leave us?
No one can predict what vast new continents of knowledge the future of science will discover. But we know that as long as men are free to ask what they will, free to say what they think, free to think what they must, science will never regress, and freedom itself will never be wholly lost.